never seen these numbers in my life.
What's the numbers?
Yeah.
All right, Joel, Bree, Haley, Morgan. All right, good percentage of us are out there in video land. Welcome to our class. We are going over the homework problem, and it is the one that gives us some body weights and backpack weights, and we were doing a test on that. So we learned on Friday that this is how you come up with the test statistic, but you need something to test. So we set up a hypothesis, and we always start out with the slope of the line for the whole population is 0, meaning there is no linear relationship, either positive or negative. It's just a flat line. So on this one, it didn't lead us to say whether it was a positive slope or negative linear slope. The problem only mentioned linear. Is it linear or not? So we didn't know whether to go greater than or less than, so we stuck with is not equal to. All right, so in doing that, the degrees of freedom, which wasn't clear, you had to remember from chapter 3 that there were 8 backpackers, led us to a degree of freedom of 6. When we put those numbers, Kevin, give me the numbers that you put in here. T equals what?
T equals 0.09080
minus B naught. 0. It's always going to be 0 for us. Over, and what's this number?
Over 0.02831.
All right, where did you get those numbers from?
From the mini tab.
Mini tab. All right, so when we put those in, we got 3.21. So at a degrees of freedom of 6, that led us to 0.005.01. So Shannon, is that the complete answer?
No.
Why?
Because it's only half of the tail. You need both sides of the tail.
Right, this is a two-sided question. Means we want 2 tails. So this gave us, this chart B only gives us 1 tail. So Shannon, what's the true answer?
The true answer is 0.01, 0.02 because you have to multiply by 2.
Right. There's no subtract from 1 because the actual B chart gives us the value above. When we're in the Z chart, which is chart A, it gives you the bar below. That's when 1 minus comes out to play. No 1 minus here. So we did have to multiply these by 2. All right, so Maddie, if we're comparing that against alpha 0.05, what does that lead us to do with our hypotheses?
So 0.05 isn't in there, so we...
Well, this is not that kind of... We don't look for it in there. We're just comparing... We know the p-value is in here. So it might be as low as 0.01 or as high as 0.02. So we're comparing all those numbers to 0.05.
0.05 is greater than...
All right, compared to 0.05. So what happens when our p-value is bigger?
We fail to reject.
Right. We're not going to reject it. It's not that rare.
No, we reject it. When it gets less than 0.05, we reject it.
She said bigger. Not less
0.05 is bigger.
No.
If 0.05 is bigger, then you reject it.
So
What?
they're right.
You're saying 0.05 is bigger. You're saying
Glad you do.
it's bigger than 0.05.
If it's bigger than 0.05,
Talk about it. Don't touch 0.05.
I'll write it out over here.
I know, I'm confused now.
Okay.
It's about p-value.
Maddie, you're confused because the way we were saying it, I think. It is bigger than 0.05, we fail to reject. It is smaller than 0.05, we reject.
But that should make sense without memorization.
Don't think about 0.05 being bigger or smaller. Think about the thing in relation to 0.05.
Maddie, I remember it is as
So this is a problem. This is a p. Maddie, this is a p-value.
Yeah.
It's a probability of all this happening.
Right.
So it is greater than 0.05.
How is that greater
No,
than...
it's less than 0.05.
It's less than 0.05.
It is. She's right.
I was right.
When it's less
We reject.
than...
We
We
reject.
fail to reject.
No, listen. If it's less than, you reject.
Right. See, this means...
No, we don't.
Would you agree that these numbers are less than this?
Yes.
So this is as low as we're going to go without assuming that it happened by chance. So these numbers
That's
are
swimming.
below this. So these numbers, this probability is
Got it.
so low.
So we reject.
Do you
The
got it?
probability of this happening is so
I
low
remember this,
that
it's
we
big,
are
we
going
like
to
it, we accept
reject.
it.
Okay, got it
All right,
now.
It's big, we
so-
like it.
So P is a,
Wait,
so
alpha
we
is
So you're
big.
right.
No, P value is big. We like it. We accept it.
All right. So if we reject H sub O, what's another way of saying that? So
We accept
Kevin, you're good at this. If we
Oh.
say this is not, we're rejecting this, so we say,
Because there is enough evidence to say that H sub A is true.
all right, and in this case, that is to say
P
there,
is not equal to
which is, what is that saying about the linear relationship?
It's a positive linear relationship.
Makes it
if
sound
we
like you can't show
calculate
her
a
picture
body
too.
It might
weight.
not be positive.
It's a linear, it's
There is a linear relationship,
Yeah, like
but
a-
we don't know if it's negative or positive from this test. All right? All right. All right, please stop your talking so the video comes out nice for so many of us. All right, then they ask a pretty interesting question. Now that we know all that, so we're rejecting this, and we're saying there is enough evidence
Do you need
to
them all?
say that there is a linear relationship between body weights and backpack weights. So let's read number 2 and discuss it. Ryan, read about the question number 2 for this.
Would a 99% confidence interval for the slope
Your
data
own
of the
neck.
population regression line include 0? Justify your answer. Are you doing calculations?
So 99, there's always this running comparison between a test and a confidence interval. They love these questions. The AP test loves these questions. Your tests love these questions. So we need to be able to nail these questions. So we have this conclusion. We're rejecting H sub O at what was alpha, Andrew?
B equals 0.
No, alpha. What was
Oh, sorry, 0.05.
0.05. So now they've changed it. Can you tell what alpha is now in number 2? It doesn't tell you, but you should be able to infer what it is.
Oh,
Andrew?
is it 0.01?
Right, now tell everyone where you got that.
It's because it's 1.
Did they see that
1
question?
minus 0.99.
Is it showing up?
Hey, you know it has a zoom thing.
We're
It was
doing,
at a
that's
different angle.
a quick zoom there.
That's how-
We're doing number 2, and we're finding that the alpha is hidden in that 99%. And so what is alpha now?
0.01.
All right, so now we're not comparing to 0.05, we're comparing to 0.01. So if the p-value is between 0.01 and 0.02, and we're comparing to 0.01,
now it's confusing.
now what do we do?
I've already.
Now
Wait,
we
it's in
fail
it.
to reject.
Now we
Alright.
fail to reject.
Yes, yes.
Wait, yes.
Because the plausible p-values are
It's
now
in-
higher than 0.01, so it's not so rare. So we failed
Yeah,
to
think of it
reject.
like-
But they went on and asked what? What did they ask, Ryan, besides that?
Would it include 0?
Would that confidence interval include 0? We've already said that we're going
No.
to fail to reject. So would there be a 0 in the confidence interval?
Oh, wait.
So confidence interval has nothing
Right,
to do with the p-value. It's all the plausible slopes. So
This is
remember,
p-value.
confidence interval
P-value is
is
greater.
all
We
plausible,
always fail to reject if it's less.
believable,
It's
possible
usually 0.05.
slopes
So just don't think about
are going to be from this
Alpha
number
being
to
greater
this
than
number. Will 0 be one of those if we are in the situation where we are failing to reject this, which says there's no relationship between the two? So does this have to appear in this?
Yeah, it does.
It does. Ryan, can you explain that?
Because, hold on. Because 0 is in there, because we're looking for the true, hold on. We're looking for the true.
True slope.
The true slope. So if
Now we've changed
has to
this.
be in there.
Right, we're
Because
failing.
the confidence interval is that the true slope is in there, so 0 has to be in there.
Right, it's true.
Got
All right, so they love this comparison between confidence interval and test. So I hope we get you. We'll practice
Can you
those
say it
more.
one more time?
Yeah.
Why?
All right, so are you okay with this new information when we take the p-value that you gave us when you doubled it and all that? We're comparing it to 0.01. You're okay from changing the outcome from rejecting to failing to reject?
Yes.
All right, so if we're failing to reject this, that means this is, that's their, I'm not going to say accept, but it's as if we're accepting. At least we say there's not enough evidence to say this. So we're close to accepting this. So if you are accepting this, and then we go over to confidence intervals, and these has all the plausible slopes in it. And we're saying this is the slope, 0 has to be in here.
So if I said it does include 0 because we accept ipsimo, which says b equals 0.
Right, well I would mark that wrong, but that's a goes that I think I would take off because accept. Just you'd have to say fail to reject. You'd have to say fail to reject. So there is a difference between, it's like saying someone's on the witness stand and they've perhaps committed a crime. Is there a difference between saying there's not enough evidence to say he is guilty and he's innocent? There's a difference, a shade of difference between this. In the system, he's innocent. But in real life, failing to say that he is innocent is not, I mean, failing to say that he is guilty. I got it mixed up myself. All right, so you got someone on the witness stand. We are failing to say that he is guilty. Is that the same as saying he's innocent? No. It's in the eyes, he's still going to walk free, so it functions like he's innocent, but it doesn't really say he's innocent. It's the same thing
No,
as
what?
he is.
If you say someone is, if you fail to say that they're guilty, there's no other
It's-
option.
it's just-
might not be.
It's just about the wording and like how it would be received. Like if somebody was like, we found enough evidence to convict him, and then they also said we didn't find enough evidence that he was innocent.
Yeah. You think about it, you'll
That's
see
why they
there's
say
a
he-
shade of difference between the two statements, and that's why I always whisper, except. It's not a true, there's really not enough to say except, there's just not enough to,
When they announce whether the person is going to jail or not, they say that we find this person not guilty. We don't say, hey, we find this person innocent. Because there
Right.
might be a little bit of evidence that person might have been there.
so there's
So he's
not
not
enough,
guilty.
there's
He's
not
not
enough
innocent,
to
he's
say
not
that he's
guilty.
innocent. Anyway. Let's look at the mini tab. I have a very interesting point to make now. Look at the mini tab that came with this backpack situation. Do you see some numbers staring at you now that have quite a bit of meaning?
TP. You know what that means? Dancing.
Right. Look at the TP. Look at the columns that start with T and P. Do you see something of interest compared to what we have on the board here? So, what am I aiming at? Andrew, what do you see?
Is it maybe that T is significantly bigger than P?
No, what is T? What did
T
we
is the mean, and
What
P
did
is
we find?
the
T is 3.21. Do you find that number staring
Oh,
at
it's
you?
right there. Oh, it's right there. Miss Power. I didn't even need to do it. It's right there.
Circle it. Circle it.
Something's useless?
So,
Oh my gosh, and that's the p-value.
Right. Oh.
very good.
Oh my gosh.
We found out, can you show, oh you are.
Yeah.
All right, we found out that the t-value was already there for us. We didn't have to do this huge calculation.
Wow.
And then the p-value, even in this state, was found. What did they get? Did they get something
They
in
got
our
.006. So they got close.
0.06 was in between.
Right.
So,
No,
so there it is.
0.018.
No, 0.108. 0.0.
Oh,
Yeah,
sorry, sorry.
Yeah,
it's the one, it's always the one on the slope line.
Yep, sorry.
Alright, so 0.018 is definitely in here. 0.006 isn't. Alright, so circle those two. They have important meaning to you. 0.028, I'm sorry, no. 3.21 under T, and under P, 0.018. We didn't even have to do this work. So let's see if that holds true. Let's go back to the crying babies. Back we go. Turn the page over. Doesn't work for the crying babies.
Check.
I had a big thing for the crying babies.
Oh, it's right there. It's in this one too.
Check and see.
Wait, that
I
interval was.
hear some hesitation.
Yeah, that interval is not as no.
All right, here's the crying babies.
28.37.
Dan, here's the crying babies.
There you go. There they
The
are.
question is, what did we get? Can you check your work,
wait,
Maggie?
I'm sorry.
What did we get for the T score
Well,
for
we
the
did
crying?
3.07.
3.07's there, so circle that. But what about what did we get for the P score
Well,
for
we
the
got
crying?
0.001 and 0.0025, but we didn't multiply by 2.
Well, in that case, should we have? I think it was one-sided.
Yeah, it's greater than.
You don't-
So,
All right, so you don't. We weren't supposed to multiply by 2. So why is this chart telling me that the p-value is 0.004 and we got an interval
Wait a
of what?
minute.
What did it
Okay.
say?
What is it?
0.001 and 0.0025.
0.001 and
Is it
0.0025?
because we're doing greater than, you have to do 1 minus?
Nope.
Oh, okay.
So the question, the answer to that question is, these mini tabs are always two-sided. They don't know what the question is. So since our question was one-sided, what could we do to quickly get the correct p-value?
Divide by 2.
Divide by 2. Circle that and say divide by 2.
So mini
And
tabs are always
make a
two-sided.
note by the mini tab that every mini tab p-value is two-sided. So if you want to use theirs and your question is one-sided, you have to divide it by 2.
So all mini tabs are two-sided?
All mini tabs, they're very stupid creatures. They're always two-sided. All right. All right, so I have a homework problem for you to do that is like that. And I will just, I
Yeah, I
copied
drew a
it from the
homework problem for
book.
class.
If you want to take your book home, you can, but I copied it from the book. There's no mini tab. You're gonna have to do the whole thing. You're gonna have to do liner. You have to check the and when you pull up a graph on your calculator under for liner, I want you to tell me what you pulled up and check it whether it met the requirements or not. So this is your homework problem. So tuck that away, and you'll be doing a test and a confidence interval. So this will be good practice. You're welcome. All right. So good luck with that. See if you can pull it all together. We're going to go on to the next topic. So tuck that away. And
Do we get new day notes?
we do.
Yes!
All right. One thing I need you to do when you get your notes is,
It's a parenthesis and a comma. And another parenthesis.
well, let me give you your notes and I'll tell you what to do with
For
it.
educational purposes.
There's a mini tab missing that I actually want you to tape in as a flap. Let's see what I mean by a flap. All right.
Yes, oh yes.
Those are mine.
All right. So because the
This
mini
one's like way
tab
bigger.
did not make it onto the paper, I'm giving you a mini tab flap. And here's what I mean by a flap. On this paper, turn over to this page. And I'm going to actually make a flap because you need some room to work. So I don't want you to cover up the workspace. I want you to actually make a flap. So when I say that, all you do is take a piece of tape. One piece is all you get.
Staple.
And you're going to tape it to the paper so you can flap it. All right?
Ooh.
Can I use the stapler?
A little
You're gonna get a
flapper.
flapper. All right,
It
so
might actually be easier.
Ryan, I'm using
take one
this.
piece of tape.
Okay.
Because then you'll have to bend the flapper Whereas tape, you could just pull up the whole thing with the tape.
Come on.
Alright, and you can
No.
show me where it goes.
No.
The way I throw my things in my
It
mind
goes right
are
up
come on.
here.
Maybe you could just not do that. Oh no.
Alright.
Throw that out there.
Piece of tape.
Where's it go?
If it's okay, I'm gonna use this tape.
You really have it in the middle, but you're
I always
he
flap
needs
it.
to have like only one
So
eye.
flap, I think. Right here in the middle, right?
Flap.
Oh
He's
yeah.
really doing
You got
some
to see
face.
the chart under it clearly.
If I flap it, I will, yeah.
Alright.
He just ate his.
Take one piece of tape and.
No, wait, this is cool steak.
Graphics.
Flap. One piece, tape.
Right over top of these charts.
Yeah, but so that you can just,
You can flap it up.
so you can flap it.
Maybe I should bring in some fancy
Alright.
epoxy
Wire like
and glue her to the
Fill the
wall.
whole thing with the aux cord in there?
Whole board and then for sure.
Can you, make some for those who are absent?
I've bent the hole so that it's bigger.
we still need to bring
No, so last day you need to like fill it with like hand sandwich. Glue.
Fill it with like
break it so it's
Okay. Alright, we finished.
Put an echo down.
We finished 12.1 where we were learning how to do tests and confidence intervals for slope. So now I'm going to address what to do when your data, when you go to check your data, underliner, and it's not linear, it's curved. So I know you've been worried about
Mr.
that.
Howell, let me guess, do we just assume it's not curved?
Nope.
we just pretend that
We
it's
just
30.
entirely ignore it.
We're gonna
Where's
take
the
out,
house?
believe it or not, we're gonna do some math.
Oh.
We're gonna stream at it?
We're gonna end this whole book with math.
No, Mr. Howell, that's a big
Alright.
shot.
So let's see how far we get on
So what time in the
this
year
today.
doing math?
Alright. What do we do with curved data? So if you would, go to the front of your notes and put that question on the top. So what do we do with curved data?
Dude, we told you to tape it. You ripping you paper now.
My lord was throwing your Bible.
Alright, remember for those who are listening on Video Land, let's be quiet, raise your hand when you have something to add. It comes across so much better in Video Land. What are we going to do when the data is curved? So let me tell you, the answer to that comes from your math class. We're going to transform it.
Oh.
Alright, we're going to transform the data, and for example, suppose you start with a power model. That means something like this, a power model. There is another model, but we'll just start with the power model, and that is like this. Y equals some constant, A and B are constants, X is a variable, raised to another constant. That's an example. It's not all that exotic. It's like pi r squared, where pi is your constant, r is your variable. When you eat a pizza that's 6 inches in radius, you could get the area of the pizza and by putting a 6 here, and b is 2 squared. So you could have pi 6 squared. So that ends up to be 36 pi. So what if it becomes a 7-inch pizza? So then you have pi 7 squared. So we use these kind of models all the time, but I'm going to actually give it a name. Suppose we start with a model like that. The first one I want to call your attention to is the one on the first page where we have 2 variables and they do not create a straight line. So can you find it? It's on the other page, Dan. We're on the front page of that.
The front of the
Yeah, front.
Is it under the
We're
flap?
not
There
on
it
the
is.
flaps. We're not on the flaps.
Oh.
We're on the
So
front.
the-
Okay.
All right.
the little curved one at the bottom under go
I mean,
fish.
we'll see the curve in a minute, but I need you to know what the problem is.
Yeah, you want to go first?
All right, so Maddie, would you read to us about this big problem of how hard it is to weigh fish and how easy it is to find their length? Go
Yeah.
ahead.
So, imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try and weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight.
All right, so we have two variables going. So if you can see they give you length and width in the charts, but we don't have to put them in our calculators because turning the page over, we will see that the data unflaps so you can see the curves. Hey! So let me get you
This
your
video
stuff.
was for you.
Do we have
Joel
one
and
that's
Morgan.
flapped for her?
Hey, Morgan, where you at?
All right,
Joel, where you at?
here we go. All right, so, thank you. Unflap the second page and look at the data. Can you find the chart that has length of fish in centimeters here and weight of fish in grams here? Is that data curved or is it straight?
It's curved.
Where are you?
Yeah.
Oh, it's on the front. I'm sorry. I had to
Oh.
turn
Oh.
over.
Yeah,
Okay.
and the goldfish
All right,
Then
it's
it's
on the page
curved.
one of your
Curved like
notes. So
That's
we're
curved.
addressing curved data today, and we're going to see how to transform it until it is straight data. One of
Straighta.
the power models, there's several ways we can address this curved data, and on this one, we're going to see how this one can be straightened two different ways. So the first way to straighten it is we can take each length and we can cube it. Turns out, is that what they did? Can you see
The next
graph?
page.
Yeah, the next page.
Yes, they did.
They cubed the length, so we're in
Under the flag.
centimeters cubed, and the weight is unchanged. It's still in grams. So, so Andrew, did that straighten the data up fairly
Yes.
well?
It did.
All right, so we went from curved data to fairly straight data just by taking the length and cubing it.
How did that work? Because if every single one is cubed, why did it
Because
change?
it's still matched to the same
Oh,
weight.
because it's the same
We
grams.
didn't change that.
Okay.
All right, but there's another method. Can you read the graph and tell me what the other method was as well? All right, Andrew.
Taking the square root of the weight.
It wasn't square, was it?
Or cube root, sorry.
All right.
Is there a reason
Any
it's
notes?
only cube?
Kind of. We just
Yeah,
got
these are
this
the only
new.
notes we've taken so far.
Yeah, not really.
And
All right.
We went over the homework problem.
Yeah, that was
All right, so
But that
did
was pretty much it.
did that straighten it out as well?
Yes.
All right, so why are we so impulsive, insistent, demanding on taking curved data and making it straight?
So it passes liner.
Yeah, and so we can use regression to use it.
Oh.
However, it doesn't change the line altogether. So let me give you some training. Over here, we couldn't use liner at all. So if we had y hat equals a plus bx, and we put in the data, the calculator would give us an a and a b, but it would be meaningless because it didn't pass liner. So we can't use it over here. But over here, we can use it, but the equation has now changed. It's not y hat equals a plus bx. It is now y equals a plus bx cubed. Do you see on the first transformation where they took the x value and cubed it, that now shows up in our linear regression. So I'm going to put in the meaning for this. So weight, expected weight equals a plus b, and then we had length cubed. Let's give it some more meaning. Can you look at mini-tab for this scenario and tell me what a and b are, so we'll even bring it home even further. So Maddie, look at the mini-tab that is on the flat probably, and I want the one that has length cubed, and can you find the appropriate a and b?
Okay, so A is 0.01467774.
It is for that one?
Is that
For
wrong?
weight cubed?
Length cubed weight, like transformation 1?
Yeah, this is length cubed.
There's not a weight cube.
Alright, I meant length cubed.
Okay.
Alright, so I guess that is length cubed. Length cubed. Why do I have the other numbers? Let me just look at the mini tab. Alright, so the first one I took length cubed. Alright. Length cubed. Okay. That's the one. I don't know why I don't have those numbers. Okay. We'll find out in the wash when we put a number in, because I do have the answers. Alright, so give me those numbers, not the numbers I have. So we're looking at the mini cube, the mini tab that use length cubed versus weight. So once again, Maddie.
Okay. 0.0146774.
0146774. Alright, and that's your A?
Yeah.
Alright, let me get over here. Plus, what's your B?
Wait. 4.066.
Is it that high?
No.
It's the constant, right?
This is the constant. Did you give me the wrong one?
Did I?
That's what it is. That's why mine isn't in green.
I was looking at the wrong
Alright,
one.
now
I got
we're, okay, give me the constant.
Okay.
Now we'll be
The
on the same.
constant
Okay.
is 4.066.
Alright, that's what was messing me up. Okay, and now the slope.
And now the B is 0.0146774.
Alright. And remember, the variable is length cubed. Alright. So do you see how the regression line has now changed? In order to straighten this curved data, we have to cube whatever's on the x-axis, because that's what created straight data. Another way we could have addressed it is to look at it this way. So having trained you how to do the regression line, can you take this one, Kevin, and give me the correct regression line for where we did it a different way? We left the length of the fish alone, but we took the cube root of their weight. So we want y hat equals a plus bx for this situation, but the y hat is now whatever was on the y position cube rooted. So can you walk me through a similar regression line?
Length
Right.
is going to be negative 0.022.
All right, but first of all, I need to know what to put here for y, cube root of y. So what's the more meaningful variable for this scenario? What's on this axis?
Weight.
All right, so we're going to do the cube root of the weight with a hat on it equals, now you're up to where you get your A and your B. I got it.
Negative
All right.
0.022.
All right, he's correct. Would you have picked that number? All right, that's your A. And that's from the other mini tab on your flap. Okay, go ahead.
Plus 0.2466.
1/6. And then what is the more meaningful, instead of putting X here, what will I put here for the variable? I ran out of room, but I'll squish it on here. Length. It's not cubed this time. It's just regular. All right, length. All right. So let's see how good these regression lines are. So say I took my floppy fish that I can't weigh, but I can find its length, and I find out that it is 36 centimeters long. So first of all, I want you to use this regression line right here. For length equals 36 centimeters. Go ahead and predict the weight using this regression line. So everybody, Kevin, grab it. 4.066 plus 0.0146774 times 36 cubed. So, give me that number and we'll bounce it off of each other till we agree. Anyone got it? We're putting 36 into this regression line.
Hi.
Thank you.
Thank you.
Morgan, you're back.
688.5.
Okay. Kelly, what
Who's
you got?
bouncing? Anybody gonna bounce?
688.5.
688, anyone confirm?
Who's gonna bounce? Ryan bounces.
I got 688.
Ryan, Haley, Brandon
Confirm.
bounces. Anybody bouncing again?
688.85,
Bounce,
and
bounce,
this is
bounce,
grams. Alright, so that's the expected value if we use this regression line that straightened out our data. So now let's put in 36 into this one. So are you mathematically trained enough to solve this for weight? So we have weight, cube root of weight equals, give me that number first. What's 0.02204 plus 0.24661636? So I need that number. Anyone got that?
8.8.
Anyone confirm that? 8.86? Anyone?
Not yet.
That's before I finish it. That's just the right side of the equation. I need it confirmed.
8.85.
All right.
Oh yeah, 8.86.
All right, so that's not equal to weight. It's equal to the cube root of weight. So
694.
so math student, what do you do to each side?
Cube it.
Cube it. All right, so when you cube both sides, you've been well taught.
Cube
Kevin,
it.
what you say you got?
694.6.
694.6
Cube it.
grams. So, what do you think?
Pretty close.
Not too bad.
Not too bad.
Not too bad.
It's about 6 grams of difference, so that's not too bad.
Alright.
So, the question is then, let's stare at the mini tab on the flap, and this will be our last
Put the flap
question
down.
for today. Put the flaps down.
Flaps down, everybody.
Flaps down, everyone. I want you to
Flaps down,
stare
everybody.
at the flap in the flap down position and tell me which one is the better regression line. There's one that is clearly the better regression line. Can you find it in your flap?
Wait, how do you know?
Where length is cubed.
Oh.
Bottom left.
I think we're the cube root of weight.
Do you see any clues in there? Your flap has all the secrets.
Oh, it's in the flap.
You're looking at the two mini tabs.
Probably bottom left.
So which one, not looking at the residuals, but looking at the information on the mini tab, there's one that is way better than the other.
Is it the second one because it has a higher p-value?
No.
I think it's the first one. Everything.
I don't know.
99.7 instead of
I think it's the first
99.5%.
one because I don't trust square roots.
I don't trust negative numbers.
The
Well, it's not a
key-
square root, it's a cube root.
It's a cube
so
root.
you should trust it.
Is
It's
the
a
value
cube.
that is called S. S
Cube.
is the average error that we will have when we use the regression line.
What's the average error?
S is the average
bottom one.
error that we will have when using the regression line. So which one has the better S?
The bottom one.
Way better.
18.
All
Is
right,
that 18%?
so this is the winner
And
right
that's
here.
1%.
All right,
Yeah,
so
but that is that percent.
we'll pick up there. Your only homework is the handout I gave you. So Haley, you need that.
Bye, Joel, Morgan, Haley, and Bree.
Talk for a minute.
Talk through what?
About the
Sure. All right, everyone in Video Land, we are over and out.
Yeah, we are.